So today, we're going to find out what the best video game of all time is, using math and programming. So be sure to stick around to the end of the video to see the final list. But first, I should tell you why I wanted to make this kind of list in the first place. Well, when I'm not running this YouTube channel, I work full-time as a computer science professor at a research university. That means I teach courses and run a research lab. And my courses are typically on themes relating to simulation, AI, and computer graphics, all of which are closely related to video games. Much of my research covers these same themes and frequently makes use of technologies originally created for gaming. Maybe ironically, all the responsibilities that stack up due to my job as a professor mean I don't really play video games that much anymore, and I've kind of lost track of what games are out there inspiring the new generation of students coming to my classes or joining me as a researcher. But there's good news. I'm on sabbatical this year, which means a break from my normal university responsibilities, and I want to use the time, in part, to check out the greatest games I've missed. But how do I find the greatest games? Well, even on sabbatical, I'm still a CS professor, and I want to take a data science approach. Step one is finding as many best game lists as I can and typing them all up as a data set. This might take a little while, so I'll see you on the other side. Actually, it took a long while. It took over a week to find all the ranking lists, type them up, and look up the publication information for all the games across all the lists. I actually found multiple different types of ranking lists. First are annual awards. Here I included the Game Awards, the Game Developer's Choice Award, my favorite because they had let me vote, the Steam Awards, which I think are the only player-voted awards I included, and Popular Mechanics, which did a retrospective Game of the Year for every year from 1971 through 2019. You can't actually use just Game of the Year lists to create an all-time ranking of games because they don't allow you to compare games between years. So the next type of list we have are the greatest games of all times list, a tradition which dates back to video game magazines from the 90s. It's kind of fun to look through these older magazines to see how opinions have changed over time. For example, here are the top 5 games according to the 1995 issue of Flux magazine. First, we have Space Invaders, which they say will kick down the front door of what you call reality and shake you until your brain screams for mercy. Which, wow, if that's how you experience Space Invaders, I can see why you'd put it at the top of greatest games of all time list. At number 2, we have the original Legends of Zelda, number 3, Doom, number 4, Sonic the Hedgehog, and number 5, Mortal Kombat. After finding a list, I need to type up the rankings in a form we can process like shown here. For games with many similar versions, like annual sports games, I rank the series as a whole. But we don't just want this one list from the 90s. I found over 60 different lists of best games of all time, spanning right up through last year, and I've included them all here. So the last kind of ranking we can find is a best games within a genre list. And I grabbed a few recent lists of best fighting games and best shooter games. Altogether, I included 6 genre-specific lists, 61 best of all time lists, and 89 Game of the Year lists. That's about 150 lists with around 7,000 total ranking entries spread across 1,342 unique titles. That's a lot of data. One way to combine all these lists is just take the average place for each game in each list. For stability, I only considered games that were on at least 3 different lists. With this very simple approach, Baldur's Gate 3 comes out on top, showing up on multiple different Game of the Year award lists, always as first place. In all fairness, I hear Baldur's Gate 3 is just that good, and maybe deserves to be considered as a candidate for the best game ever of all time. But looking at the top 5 games by this ranking, we can see that the method really biases us towards recent games that only appear on a few lists. We want a method where giants that have stood the test of time have a fighting chance. Also, mathematically, placing third on a list of games from 2022 is not as impressive as placing third on a list of 100 greatest games of all times, and simply averaging lists misses this difference. An alternative approach is to count how many times a game has appeared on any list. Here, Tetris has been on an amazing 58 out of the 61 best game of all time lists I could find. It's truly a superstar game. Honestly, I think this list of best games is great, but now we have a bias in the opposite direction. Not a single game from the past 20 years has made the top 15. Older games have a much better chance of being on more lists, just simply due to being around longer. Another issue with this method is that appearing very low on a list counts just as much as appearing near the top. We can refine this a little bit by only looking at top 10 titles for each list. For example, Final Fantasy VII shows up somewhere on nearly 50 different greatest games of all time list, but normally not near the top. It seems like people love it, but always love something else a little bit more. So re-ranking this list by appearances in top 10 sees it drop from 8th down to 15th place. We also have new games on the list, like Super Mario Bros. 3 and Super Mario Bros., that sometimes get left off of greatest of all time's list because the lists get filled up with too many other great Mario games. But when these games do show up, they often show up in the top 10. We can also see some more recent games like Resident Evil, Red Dead Redemption, and Breath of the Wild that have almost as many top 10 appearances as Super Mario Bros. Or Super Metroid, despite being much younger than these games and having had less of time to show up on top lists. That suggests that these games are actually more highly rated overall if you could somehow adjust for the age of the game. So, what's the plan to account for all of this? I think I have a clever idea. So we have different lists, each giving different rankings of games, with some games overlapping between lists and some don't. What we want to do is harmonize all of these separate rankings into one mega ranking of all the games across all the lists. To understand the problem better, let's look at two example ranking lists. List 1 rates Mario Bros. 3 as first, then Tetris, and finally Pac-Man. List 2 says Half-Life 2 is best, then Mario 3, and then Last of Us. If we take these rankings as exact and fully accurate, how can we combine the two lists? Well, we know, between the two lists, that Mario beats every game except Half-Life 2. So that suggests that the top game is Half-Life 2, followed by Mario. But then what? Well, we know Tetris is better than Pac-Man, but we have no real idea how either of them compares to The Last of Us. So as we try to zip together these lists, we have two kinds of problems. One is figuring out how to represent the ranking data from all the lists simultaneously, and the other is finding a way to represent our uncertainty about where a game should be ranked. Once we can solve these two issues, we'll have our list of greatest games. So the first thing to address is how do we combine the information from different lists? Instead of viewing each list as an absolute ranking, we're going to reinterpret the lists as a series of pairwise comparisons. So we don't think of list 1 as telling us first, second, and third place. Rather, it tells us Mario is better than Tetris, Tetris is better than Pac-Man, and Mario is better than Pac-Man. Likewise, list 2 tells us that Half-Life 2 is better than Mario, Mario is better than The Last of Us, and Half-Life 2 is better than The Last of Us. If we take every ratings list and break it up into pairwise rankings, we can then combine all of these pairs into one super list that contains everything we know about the relative rankings of all the games across all the lists. Not all of these lists will agree with each other. For example, Half-Life 2 and The Last of Us appeared jointly on 25 different ranking lists, with their relative placement changing from list to list. But overall, Half-Life 2 was ranked higher than The Last of Us on almost 2/3 of these lists, so we'd probably expect Half-Life 2 to end up higher ranked overall on our final combined list. Once we've loaded a dataset of all game ranking lists, the actual code to extract pairs of rankings from these lists is pretty straightforward. First, we'll loop through each pair of titles in a given list. Then, the one with better ranking, lower number, is marked as the winner, and this match result is saved in a big list of all matches. So now that we know how we're going to combine all the lists as pairwise data, how do we actually represent the ranking in a way that accounts for the uncertainty in our knowledge? Here's my idea. Instead of ranking each game directly, we're going to assign a score to each game title that captures how great the game is based on our dataset. Titles that show up at the bottom of lists will have a low score, and titles that consistently rank at the top of many lists will score high. At the start, before we've processed any of the data, we can think of every title as being in the middle of our rating spectrum. But even better is to explicitly represent our uncertainty with a bell curve, a Gaussian distribution, that encompasses the range of possible rankings. As the title is involved in more pairwise matchups, we can shrink the width of this bell curve, that is, shrink the standard deviation of our Gaussian, to represent our increasing certainty about the title's strength with each new observation. For example, let's look at Super Mario Bros. 3. Before we've processed any of our ranking data, we can use a very wide Gaussian to represent that our game might have any ranking possible. Our first data point was that Mario was ranked higher than Tetris. This means we shift the mean of the distribution to the right to represent a higher score. but also shrink the distribution's width a little bit as we have a little less uncertainty about the game. The next data point is that Mario beat Pac-Man, so again, we move Mario's curve to the right and shrink the Gaussian distribution as we gain more confidence, which I'm representing here as the Gaussian getting narrower but taller. Next is Mario losing to Half-Life 2, so we move the Gaussian left and shrink the uncertainty even further. And finally, Mario beats Last of Us, so we move back to the right and shrink the uncertainty even more. You may have noticed the last two movements were smaller than the first two. As we get more confident about our rating, we have less a priori uncertainty with each new data point, and so it'll have less impact on the estimated strength of the title. After seeing Mario Bros. 3 beating 99 other games, the 100th result will have only a small effect on our opinion of Mario, win or lose. Looking at all the data from our combined two example lists, if we run the same process for Half-Life 2, it ends up ranked just slightly above Mario, but with a wider uncertainty as it had fewer matchups. Tetris gets some credit for beating Pac-Man, but it ends up well under the other two titles after losing to Mario. And finally, Pac-Man and Last of Us end up basically tied for last place because they both lost all of their matchups. Last of Us ends up slightly higher as it lost to stronger games. This type of approach is rooted in a branch of statistics called Bayesian estimation. Here, you represent something you want to estimate, in our case the game's strength, as a distribution called a prior. Then, with each new piece of data, you update the estimated distribution by balancing the uncertainty represented in your prior with your confidence in a new piece of data. The exact equations used can depend on various assumptions, but I can talk you through a streamlined version of what I used for rankings. The process is iterative, so we first start with our latest estimate of each title's strength. Here I show an example with red on the left and blue on the right. Before looking up which title actually did better in our dataset, we can predict who we think likely won based on these prior distributions. In this case, the winner is almost certainly going to be the blue distribution, labeled as N1, as it's so much further to the right, especially relative to its small uncertainty. We can compute the exact probability of blue's win with the difference of Gaussian's formula, where phi is the cumulative distribution function. After we have our predicted winner, we can check out the actual winner in the dataset. Let's assume our prediction was right, and blue won. We'll update the center mean of the Gaussian distribution, represented with the Greek letter mu, based on this equation. K is a scaling factor I can come back to in a second, but the secret sauce is R minus P win, where R is the actual result, 1 for a win and 0 for a loss, and P win is the probability you expected to win. So if we win, like blue, R will be larger than P win, and our score goes up. If you lose, like red, R will be smaller than P win, and your score goes down. Another implication of our update equation is that the more unexpected the win was, the higher the gain is. For example, if red had won instead, this is a very unexpected result. So R minus P would be large, and we'd see a big update. Importantly, the whole system works because when your actual win rate matches your predicted win rate, then R minus P will average out to 0. Our predictions are accurate, and we'll stop changing our estimated strength. The job of the scaling factor K is to balance the impact of uncertainty between the two distributions as shown in this equation. If the winner and loser have about the same uncertainty, K will be 1/2, and both distributions will be updated equally. But if one distribution is much less certain than the other, then the one we're less certain of will have a bigger share of the update. Finally, we also need to update the uncertainty of the distribution itself, represented by the standard deviation sigma. Here is the equation for the new sigma 1 tilde given the old sigma 1 and sigma 2. If you have any familiarity with math, you should try to prove for yourself that this update equation always shrinks our uncertainty with each new piece of information. That is, prove that the output, sigma 1 tilde, is always smaller than the original sigma 1. You should also try to show that if the uncertainty of sigma 1 is much smaller than sigma 2, then sigma 1 won't change that much. This makes sense, in that if you're sure of your rating and your opponent is unsure of theirs, you probably shouldn't treat either winning or losing to them as very informative. The code for all of this is very straightforward. I simply iterate through the matches we created earlier, then run our update equations for each matchup. What we've created here is an example of a skill estimation algorithm. The most famous of these is the ELO system, invented by physicist and chess enthusiast Arpad Elo. The ELA system was popularized by its use in chess to rate the relative skill of chess players starting in the 1960s or 70s, and has been more recently adopted to many other sports. More recent variants of the basic idea, such as Glicko and Glicko 2, have been very popular for matchmaking in video games like Counter-Strike, Dota 2, or even Chess.com. Because once you estimate your player's skills, you can try to match similarly strength players with each other. My favorite skill estimation algorithm is actually a proprietary algorithm from Microsoft called TrueSkill, which is used in matchmaking games on the Xbox network. But all four of these methods are fairly similar, representing a player's skill as a distribution with a mean that moves higher with more wins, and an uncertainty that's represented as a Gaussian bell curve. The main difference between these algorithms is how they treat the uncertainty. In the original ELO system, everyone has a fixed uncertainty of 200 ELO points. In Glyco, uncertainty starts at 350 for new players, shrinks towards 0 with each game played, and will grow again as players take time off with no new results. Glyco 2 updates this to have an extra parameter for uncertainty that estimates how volatile each individual player is. And finally, TrueSkill adds extra parameters to count for how skillful versus random a game is, parameters to allow for the possibility of ties, and can even handle games with many simultaneous players or teams using advanced statistical estimation techniques. Of these methods, the ranking code I've used here is probably closest to TrueSkill. So we've talked about the theory of pairwise comparisons and have dived into Gaussian uncertainty and skill estimation algorithms, so it's finally time to reveal what the best games of all time are. But wait, I think I can greatly improve our dataset with a small tweak. If we look at something like GDC 2020 Game of the Year, we only have one winner, Hades, and 4 runners-up. That doesn't provide us with too many data points. But we know that many other games came out in 2022, and we can interpret this list as telling us that all 5 of these games are better than any other game released that same year. This gives us dozens of new pairwise comparisons, as we know that each winner and runner-up beats every other game released the same year. And we can do this for every game of the year list for every year. We can do a similar step for best games of all time, or best games of a genre, where we add every eligible title not on the list to pairwise matches where it loses to every title that is on the list. This augmentation takes us from about 470,000 pairwise matchups to over 6.5 million. Running our ranking estimation algorithm on all these matchups might take a while, but let's go. So which game comes out on top? Starting at number 15, we have The Witcher 3, Metal Gear Solid, Street Fighter 2, The Last of Us, and Red Dead Redemption. At number 10, we have the classic Call of Duty 4, then the beloved Ocarina of Time, then Super Mario 64, which basically invented the modern 3D platformer and is still played intensively today. At number 7, Zelda: A Link to the Past gets my personal, nostalgia-filled 90 kids vote for greatest of all time. Above that, we have Mass Effect 2, one of the greatest RPGs ever. Then Super Metroid, which helped define the genre of Metroidvania. Then Bioshock. Then the massively influential Half-Life 2. Then Resident Evil 4. And then the number 1 greatest game of all time is the 1984 classic Tetris. Honestly, you probably should have seen this coming. It was on 58 out of the 61 greatest of all time lists. And 35 different times it was in the top 10. And it ranked in the top 3 multiple times just this past year. You know, I think if I had to introduce a random person whom I knew nothing about to video games, I can't think of a better choice to start with for them than Tetris. Honestly, I'm pretty happy with this list. Even if I might personally want to tweak a few of the rankings, I think every one of these games belongs in any discussion of greatest games of all time. But I've played most of these games, and my goal was to find new games to try. So let's only look at games released in the past 10 years, as these will be much more likely to be new to me. That gives us The Witcher 3, Breath of the Wild, God of War, Red Dead Redemption 2, Hades, Disco Elysium, Bloodborne, Elden Ring, Persona 5, and The Last of Us Part 2. I've not played any of these, so you'll have to let me know in the comments how good this is as a list of the best 10 games from the past 10 years. Actually, some very recent games, such as Baldur's Gate 3 and Zelda Tears of the Kingdom, have a really high uncertainty under our model, and I wouldn't be surprised if they settled into the top 10 once we have more ranking data that includes these very recent games. Another issue I noticed is that this list is pretty dominated by 3D action games, and I wanted to add a little diversity to my gaming list. So let's look at some other genres. For top 3 adventure games, we have Outer Wilds, Return of Obra Dinn, and Firewatch. I feel like I've heard great things about all 3, so I'll add them all to my games to play list. For top strategy games, we have Hearthstone, Fire Emblem, and Crusader Kings 3. I've actually played quite a bit of Hearthstone, but Fire Emblem and CK3 are both new to me, so I'm happy to add them to my list. For top shooters, we have the original Overwatch, Fortnite, and Res Infinite. I've also played a lot of Overwatch already, so I won't be adding that. And I'm sure Fortnite is great, but I'm not really looking for a multiplayer game right now, so that leaves just Res Infinite to add to my list. For top platformers, we have Inside, Mario Odyssey, and Celeste. Again, all 3 are games I've heard good things about, so they go straight into the list. And finally, for horror games, we have Resident Evil 2, Alien Isolation, and Resident Evil Biohazard. To be honest, I'm just not that into horror games, and I can't see myself right now playing a new Resident Evil game anytime soon. But I heard the alien in Alien Isolation has really interesting AI, so I feel like I at least need to try it. Onto the list it goes. Okay, here's my final collection of games to try, and I'm very curious about your feedback. Well, I thought it was my final list until I looked up how long these games typically take to finish. Even during my sabbatical, I don't have 50 plus hours to be spending on each new game. For now, I'm planning on focusing on these 8 shorter games, but let me know if you think that's a mistake. If people are interested, I can share the full ranking list of all the games I looked at. I'd love to hear what you think, either about what games I should try or about my algorithmic ranking strategy. Also, if you enjoy a technical, code-based approach to exploring topics in graphics, robotics, or simulation, be sure to subscribe below or to check out one of my other related videos. I'll see you next time.